You have been using a normal distribution from the central limit theorem, and if we convert the normal distribution to have a mean of 0 and a standard deviation of 1, that's a z distribution. So we use a z-table, and that's called a standard normal distribution. But to do that, we need to know the population standard deviation. So what do you do if the population standard deviation is unknown? And that happens more than it doesn't. So usually we don't know the population standard deviation. So if you are doing a confidence interval and you're trying to estimate this population mean, it's unlikely that you know the population standard deviation because it's about the population. But you can calculate the sample standard deviation. But to do that, you have to use a t-distribution rather than a normal distribution or the z-table. So now a t-distribution looks different than a normal distribution. It doesn't look like what's on the screen. I'll show you what it looks like in a second. But to understand why it looks different, you need to understand the distribution of sample standard deviations. So when you calculate a sample standard deviation, it's not going to be exactly the population standard deviation. What's going to happen is that more likely than not, the sample standard deviation is going to be more than the population standard deviation. If you remember, when we calculate the sample standard deviation, we use degrees of freedom. So we do n minus 1. And we do that because a lot of times the sample standard deviation underestimates the population standard deviation. And the degrees of freedom fix that a little bit, but not enough. And so we still, even after that correction, we have a distribution like this. It's not bell-shaped, it's skewed to the right. So the main point is the sample standard deviation most of the time is going to underestimate the population standard deviation. And that's because the points are going to be closer to the sample mean than it is the population mean because it's from that sample. And if you want to know more about the degrees of freedom, you can kind of go back to when we learned about the sample standard deviation. Here is the student's t-distribution, or just called the t-distribution. And the normal distribution is the yellow. It's the one with the skinniest tails. And then t-distributions have fatter tails. And so, but both a normal distribution, or the family of normal distribution, and the t-distributions are special types of bell-shaped distributions. A normal distribution has a different shape depending on its mean and its variance, or its standard deviation. And the t-distribution also has different shapes depending on the mean and the standard deviation, but it also depends on its degrees of freedom. And the degrees of freedom are calculated by taking the sample size minus 1. And the higher the degrees of freedom, the more the t-distribution looks like a z-distribution or that normal distribution. So the more people you have in your sample, the higher the sample size, the more likely your sample standard deviation is going to reflect or be closer to the population standard deviation. It's not going to underestimate it as much the more people you have in your study. So if you have a lot of people in your study, then you're going to have a high sample size, and your t-distribution is going to look very close to a normal distribution. And If you have enough people, then you can just pretty much use a Z distribution rather than a T distribution. But you have to have a lot of people. So you see here, the higher the degrees of freedom, the closer it looks like a normal distribution. This is a good time to talk about kurtosis. A T distribution has what's called a negative kurtosis. So on each of these distributions, there's 3 of them. These are where the tails are, if you remember when we talk about shapes of histograms. And if it has a negative kurtosis, the tails are fatter. And if it has a fatter than a normal distribution would. And if it has a positive kurtosis, then the tails are skinnier. And then in the middle you have the normal distribution. And you can calculate a statistic for kurtosis. And you can do it by hand, and you can also do it in Excel. And Excel will give you a number that's, either 0, negative, or positive. With 0, then it's a normal distribution. If it's negative, then it has a fatter tails. Then a normal distribution. If it's a positive number, then it has skinnier tails, then a normal distribution. Now keep in mind, this calculation, the statistic is all based on the tails, not the peakness. So a lot of times the peakness will change too. If you have fatter tails, then the data is kind of going away from the middle and going to the ends. Or if you have a high peak, then you don't have much as tails. But really, kurtosis, the calculations all based on the extremities, or the tails.